So today I'm gonna be presenting another beautiful article from Chris Dyer, which is this article, Compositional Character Model for Open Vocabulary Word Representation. So this article in 2016 by Chris Dyer and others. And so if you like this article, with high probability you also like this article as well, that I've explained in a different playlist. So morphology is really important because words are made up of morphemes. So it has a base, it has a prefix and suffix. So you can take advantage of that in your word-to-vec embeddings. For example, when we say unreadable or retaker or take away. So the idea is composition of characters for word embeddings. So each character has a different embedding and we augment them. So relative to traditional word representation models that have independent vectors for each word type, our model requires only a single vector per character type and a fixed set of parameters for the compositional model. Despite the compactness of this model, and more importantly, the arbitrary nature of the form-function relationship, our compressed word representation yields state-of-the-art in not only in language modeling but also in part-of-speech tagging. So when we say word similarity, you can think about it as a similarity in form or functional, what is a semantic and syntactic similarity, what we used to work with word-to-vec. For example, here similarity in form, this one, similarity is form. If you just change the U to A, it becomes totally different semantic similarity between two words. But you know their forms are very similar. You just change one character. So it has pros and cons. So that's why we want to combine these two roles for a better word-to-vec. Our character-based model is able to generate similar representation for words that are semantically and syntactically similar, even for words that are orthographically distant, like October and January. But you see there are 3 months the 2 months that have a distance of, for example, 2 months. October, November, December, and January, 3 months. So the problem one of traditional word-to-vec lookup tables, so there are two practical problems with word lookup tables. First, while they can be pre-trained with large amounts of data to learn semantic and syntactic similarities between words, each vector is independent. That is, even though models based on word lookup tables are often observed to learn things like cat, kings, and queens, that is that nice example, but the model does not represent the fact that adding just a simple S at the end of the word is evidence for this transformation. This means that word lookup tables cannot generate representation for previously unseen words such as Frenchification, which is a combination of French and ification. Problem 2 of traditional word-to-vec lookup tables is that we can't store all the words. You cannot take advantage of the compositionality of the words. For example, if you combine these or adding, for example, ing to a word, these compositionality, you cannot take advantage of that. So and you have billions of words. How do you store for each of them a different vector? So that's a challenge. So this is another motivation, or let's say problem. And the compositional character to word can easily be implemented. It's based on the LSTM, which are able to learn complex non-local dependencies. So we can easily implement this in PyTorch. So you have character embedding. Before you use the LSTM, you should pack it and then unpack it here. Here, because you're using character LSTM of what has been packed. And finally, I want to explain this LSTM model. This is a standard input gate, forget gate, output gate, hidden representation, cell state. So everything is standard here. So what we are doing is the representation of word is obtained by combining the forward and backward states. So we learn these parameters. And we have a state sequence 0, and the backward LSTM receives as input in the reverse one. So this F stands for forward LSTM, B stands for states of backward. So we combine them to have a better representation. And I've used this technique of caching for efficiency. So we keep most frequently occurring words in memory. It's a technical issue. I skip it. And the application for language modeling is you can outperform state of the art. And so this is really important for not only language modeling, but also many other tasks, such as part of speech tagging and etc. So language modeling is a task with many applications. An effective language model requires syntactic aspects of language to be modeled, such as word ordering. Thus, if our C2W word only character to word model only captures regular aspects, such as prefix and suffix, the model will yield the worst result compared to the word lookup tables. And an application for language modeling, see, cats eats fish. It repeats. So you see, this is an unsupervised word because we don't need the label, and it's good for out of vocabulary word. And so we model that. For example, if you are working on part of speech tagging, you can take advantage of this character embedding. So embed it for words, and these are the results that you could use. And of course, the code is available on GitHub, and that's it.